Classified Applications Business Unit. Prior to this position, Dana worked in the design and installation of temporary groundwater remediation systems. Let's welcome Dana, who's going to talk about thermal destruction of PFAS during full-scale reactivation of PFAS-Laden granular activated carbon. Should have said GAC.
Yeah. Good morning. As he mentioned, I'm Dana Farmer, and I'm an applications engineer with Calgon Carbon Corporation. I am presenting on the thermal destruction of PFAS during a full-scale reactivation of granular activated carbon at one of our reactivation facilities. This presentation is based on a peer-reviewed study that was published last year. I'll touch on that a little more later. But I would like to go ahead and acknowledge the authors, Rebecca DeStefano, Tony DeFeliciano, Richard Minna, Adam Redding, and John Mathis. So Calgon Carbon is the world's largest producer of granular activated carbon. Actually, last month we had a ribbon cutting at our Pearl River facility in Mississippi that essentially added another 50 million pounds of virgin capacity to our production. We've been treating PFAS for over 20 years and have more than 100 installations across the United States. In addition to granular activated carbon treatment of PFAS, we also offer ion exchange medias. We have equipment services for both service and for sale. We have application design capabilities, and we have robust R&D capabilities where we can help our customers develop solutions to problems. Okay, so this is just some data on our filter-absorbed carbon, which is used in PFAS remediation. The chart here on the left is showing multiple PFAS contaminants being removed by carbon over a lot of bed volumes, and it's basically demonstrating that carbon can remove short chain and also long chain contaminants, PFBS to PFOS. The chart here on the right is showing a full-scale installation of one of our Model 10 adsorber systems. These systems are typically installed in a lead-lag configuration with 10 minutes of empty bed contact time per adsorber. The influent to this adsorber is averaging 450 ppt, and for almost 30 days of operation, we had non-detect on PFOA in both the lead and the lag vessels. So typically, media is installed in vessels in a situation where you're designing it to have enough empty bed contact time for the type of media you're installing. They're fixed bed systems of granular activated carbon, ion exchange media, or an activated clay. The contaminated water flows downflow through that fixed media, and then the clean water exits the bottom of the vessel. All the medias have a finite life of adsorption for the contaminants that you're targeting. So then the question really becomes, what do you do with the media once its useful life is over? So most solid medias can be disposed of in either by incineration or landfilling them. A lot of times they have to go to a hazardous waste landfill if they were used for PFAS removal. But granular activated carbon, while it could be incinerated or landfilled, also has a unique third option, which is the thermal reactivation of that carbon. And what we do for reactivation is we would remove the carbon from the vessel in the field, either by slurry or vacuuming the carbon out. The carbon would then be transported to one of our reactivation facilities where it would be thermally reactivated in our furnace, and then that carbon can then be reused back in another application. So there are many benefits to reactivated carbon. You can get a certified destruction of all the adsorbents on the carbon material. You would not have landfill liabilities. It's a sustainable solution. There's an 80% reduction in CO2 production in the reactivation of carbon versus the production of virgin activated carbon. And typically, it is a lower cost to reactivate carbon than it would be to incinerate it. So Calgon carbon reactivates more than 250 million pounds of carbon each year. We operate 10 reactivation facilities across the world. 5 of these reactivation facilities are here in the United States. 2 of the 5 are RCRA facilities. 3 are designated as for potable reactivation, and 4 sites are CERCLA approved. In the United Kingdom, we also operate 2 reactivation facilities. We have the world's largest reactivation site in Belgium, and then we have 2 additional reactivation facilities in China. So how does reactivation work? So the carbon is fed into a high temperature multi-hearth furnace, and the carbon is usually fed in a wet, we usually receive it wet, so it's fed into the furnace wet. It's a multi-step process where at the top of the furnace, you're starting with your lower temperatures, and at the bottom of the furnace, you reach your highest temperatures for the reactivation. So the first step is the drying of the carbon, where we're operating at about 100 degrees Celsius, and this is to remove any water or liquid in the carbon pore structure. The second step goes to 100 to 150 degrees Celsius, and this is the thermal devolatilization and desorption of contaminants. And those contaminants that are desorbed in this step would then enter our abatement system and be destroyed. The third step is the high temperature pyrolysis step. This is typically carried out between 200 and 750 degrees Celsius. And the environment in this step is very controlled to contain little or no oxygen, so we're not burning the carbon. And then the final step at the bottom of the furnace is the highest temperatures. They would operate between 800 and 1,000 degrees Celsius. In this step, it's carbon gasification. So the carbon structure reacts with the vapor in the air, and the carbon pore structure is typically reactivated. So it's creating new adsorption sites and pore structure within the carbon after all the other contaminants have been removed, so that when it exits the furnace, it now has activity again that it can be used to adsorb new contaminants. So not all carbon can be reactivated, but most of it can. And all carbon that we take back to our facility has to go through our carbon acceptance procedure. We run a very robust carbon acceptance procedure where we take back spent samples from our customers. They are processed in our laboratory. And to do this, we make sure that the carbon will meet our environmental requirements, so we are meeting all our permit discharge limits at our furnace. The carbon would not pose any hazard for our plant personnel to handle at the facility. None of our process equipment would be damaged by what's ever absorbed on the carbon. And that the final thing is that we can get a good quality of reactivated product. So these are just some tests that we typically run in our lab on each sample. We look at the spent apparent density of the carbon to make sure it's not too low or the carbon's not too soft. So when it goes through our furnace, it doesn't get beat up. For safety, we look at ignitability. We look at the type of contaminants that are adsorbed on the carbon, the halides and the sulfur. This is especially important for PFAS because we are looking at the fluorine content on the carbon. We do some radiation screening. We also look at the amount of inorganics adsorbed onto the carbon bed. And in liquid phase applications, we look at the metals adsorbed. So reactivation is a very unique process, but the nomenclature for reactivation often gets misconstrued, where some other terms, incineration or regeneration, they kind of get used interchangeably, but this is definitely not the case. Regeneration is very different, but the waste code defines reactivation using the term regeneration, so that's where some of the nomenclature gets tricky. But incineration and reactivation are similar in that they're both very high temperatures, but incineration usually has oxygen in their environment, whereas reactivation does not. and regeneration is usually at a much lower temperature. So the big difference between reactivation and regeneration, as I mentioned, reactivation is at much higher temperatures. It's a thermal process that is removing the contaminants and destroying them from the activated carbon pore structure. So after your carbon is spent, you send it through the furnace, through the reactivation process, and you are left with a reactivated product that has no contaminants left on the surface. Regeneration, on the other hand, is usually done at very low temperatures, and it utilizes either steam or maybe nitrogen or a solvent that is fed through the spent carbon bed. This low temperature process will remove some of the contaminants from the carbon. It does not destroy them, but it will free up some adsorption space that the carbon can then be put back online and used again. So regeneration is typically done in situ in the vessel, whereas reactivation is always ex situ in a furnace. So once the carbon reaches its useful life, you can regenerate it in place with steam or nitrogen or a solvent. But the problem with this is you're usually left with a stream that needs further treatment or disposed of. So our reactivation process is very unique. We start the process with a high temperature multi-hearth furnace that has many hearths to it, where the carbon is fed at the top and the reactivated carbon exits the bottom of the furnace. We also have an abatement system that consists of a thermal oxidizer, a chemical scrubber to remove any acid gases, a bag house for particulate removal, and then that is the air is then exhausted in our exhaust stack. The residence time in the furnace usually exceeds 1.5 hours. That's something that else is very different from incineration. The residence time in an incinerator is a matter of seconds versus a long residence time of 1.5 hours. So for our study, we looked at the destruction removal efficiency for PFAS. And to do this, we looked at all the inputs to our reactivation furnace and the outputs. Used the standard calculation, input minus output divided by input times 100 to get our destruction removal efficiencies. So as I mentioned, this was a peer-reviewed paper that was published last year in Wiley's Remediation Journal. You can look up the paper. It is published with open access, so anybody can go ahead and read the paper without having to pay anything. And I would highly encourage each of you to go ahead and read the paper at some point. It has a lot more information in it than we are presenting today. So what we did during our actual reactivation study is we measured the total PFAS using Eurofin's Lancaster Lab LC-MS on both the spent carbon and the reactivated carbon coming out of the furnace. During the reactivation, we also used a third-party vendor that specializes in manufacturer emissions testing and sampling to gather our samples of the vapor phase. So we sampled the gas at the exit of the furnace, but prior to the abatement system, and then also at the exhaust stack. These samples were run using OTM 45. We did liquid phase analysis using EPA method 537 on the water that is used in the thermal oxidizer. And then we also looked at the solids from the chemical scrubber and also the bag house. We used the best commercially available analytical methods that were available on PFAS at the time of the study. So the first thing we looked at was the total PFAS, and we had an average feed of 0.748 pounds per hour of total PFAS, looking at the 29 compound list entering our furnace. Then on the furnace off gas prior to the abatement system, we had a small amount of PFAS coming out, but the incremental destruction removal efficiency was 99.989%. And that was looking at a 36 compound list. And then at the stack emissions, looking at that same 36 compound list, we had a 99.993% destruction removal efficiency. And that was for total PFAS. We then looked again at the same parameters, but this time just using the EPA's health advisory limit compounds, which were PFOA, PFOS, Gen X, and PFBS. So looking at only these 4 compounds, we had a feed rate of 0.431 pounds per hour. Our furnace off gas had an incremental destruction removal efficiency of 99.996%, and then our stack emissions, we actually had a 99.999% removal. So what we showed, looking at the total PFAS, is that the furnace itself is destroying greater than 99.9% of the PFAS on the activated carbon. And then once you include our robust abatement system, we get our total destruction removal efficiency to greater than 99.99% for total PFAS. So this slide's a little busy, but this is showing the 29 compounds that were on the spent carbon, and then we tested for those same 29 compounds on the reactivated carbon. We ran 3 tests during this study. The total PFAS on the spent carbon ranged from about 92 ppb to about 119 ppb. And then the total PFAS on the reactivated carbon was essentially non-detect. We did have 1 hit for PFDA when we ran that 1 sample, but then when the sample was rerun, it came up as non-detect. And it's just good to note that there was actually no PFDA on any of the spent carbon prior to the reactivation. We also tried looking at our total mass balance for fluoride in our system. Fluoride gas, we know, is generated. It's very reactive with everything, and so it's very difficult to close the fluoride mass balance. We did calculate our mass balance at 61.4%. 100% mass balance would be much better, but since we know that the fluoride is reacting with everything, it reacts with our furnace refractory, we know it reacts with our equipment, it would be very difficult for us to get 100% mass balance. So for our conclusions and findings, it's important to remember that regeneration is not the same as reactivation, and incineration is also not the same as reactivation. At Calgon Carbon, we prefer to use the term reactivation for all thermal reactivation of spent carbon. Our furnace and abatement system has shown that it can get greater than 99.99% removal and destruction of total PFAS on spent carbon, and our testing has shown that the reactivated carbon did not have any PFAS left on it. And I'll be available for questions at the end. Thank you.